Hello, my name is Sarah and I'm an undergraduate chemistry student in Dr. Michael Ross's lab. Today I will be showcasing my research in designing multimetallic core satellite nanoarchitectures by Galvanic exchange. Metal nanoparticles have dimensions that range in size from 1 to 100 nanometers. They exhibit a high surface area to volume ratio, giving them exceptional properties not observed in their bulk forms, such as improved light absorption and increased reactivity. There is currently a widespread search for new multimetallic nanomaterials that leverage these enhanced properties for sustainable innovation. They can function as catalysts that drive reactions that convert biomass or carbon dioxide into more useful materials, such as chemicals or fuels. They may also harness and convert solar energy into chemical energy to degrade harmful organic pollutants in water, or even produce clean carbon-neutral energies such as hydrogen gas. The possibilities are absolutely endless, but how do we design these materials? As Roslab recently developed a synthesis for gold-tin alloy nanoparticles with remarkable optical and structural properties, I've spent the last year trying to transform them into new nanostructures, as manipulating their size, composition, or morphology would lead to unique changes in their properties. I first synthesized gold nanoparticles through the well-known Turkovich method. I heated a solution of chloroauric acid, and after coming to reflux, I added a small organic molecule called trisodium citrate, which reduced the gold 3 ions in solution to solid gold atoms that come together to form the red nanoparticles we see here. This reagent also acts as a capping agent that surrounds the nanoparticles and prevents aggregation through electrostatic repulsions. I then added tin chloride and a polymer called PVP to the gold nanoparticles. The solution was heated to allow the tin ions to adsorb at the gold nanoparticle surfaces, and here PVP acts as a capping agent to prevent aggregation through steric hindrance. I then quickly added sodium borohydride, which reduced the tin 4 ions in solution to solid tin. The chemical reduction proceeded under heating, and the tin diffused into the gold. I then sought to transform these gold-tin alloys into a creation of my own by incorporating palladium into them, which is a highly catalytic metal that would hopefully improve the nanoparticles' overall catalytic ability. I slowly added a potassium-palladium chloride solution to the gold-tin nanoparticle suspension. This caused a spontaneous redox process called galvanic replacement to occur, in which the tin was oxidized and dissolved from the nanospheres, and the palladium ions were reduced and deposited onto the nanoparticles. Transmission electron microscopy showed how the smooth gold-tin nanospheres transformed into more rough structures, resembling a core sphere decorated with smaller spheres, presumably made of palladium based on their lighter color and palladium's lower atomic mass. Energy dispersive X-ray spectroscopy was then used to map each element's location. There was a high amount of gold at the center, with palladium and tin more abundant near the surface. UV-vis spectroscopy then showed that the nanoparticles absorbed light at a slightly longer wavelength and lower energy in the visible region after palladium addition. Despite palladium having poor light absorption compared to gold and tin, the peak did not broaden significantly, meaning that their optical properties remain suitable for many light-driven applications. My next steps are to do more elemental and structural analysis on these unique core satellite structures to learn more about them and the galvanic exchange mechanism. I also plan to study their catalytic ability in a sustainable chemical process. I would like to thank my lab for all their support, the Kennedy College of Sciences for funding in the summer, and all of you for sticking around and listening.